Okay, good evening, everybody. And welcome to another session of organic chemistry. Now, in today's session, we are going to start a discussion on the chemistry of amines, which is taken from chapter 24 of your book. But before we start the session, let me make a few announcements. Tomorrow, Friday, April 19 at 8 p.m., there will be an online review session. And for that session, we are going to use the end of chapter 23 questions in OWL for that review session. Also, on Sunday, April 21st, April 21 at 8 p.m., we are going to have another online review session. This time we are going to review for the exam number 4, which is scheduled for Thursday, April 25. And for the seniors, for the graduating seniors, I want to remind you that your final exam is scheduled for Wednesday, April 24 at 6 p.m. in room G8 of the chemistry building. And in addition to that, the graduating seniors will come back on Thursday, April 25, to join the rest of the class to take the exam number 4. So we do have a lot of activities lined up for this coming week. And finally, I want to remind you that the homework assignment for this week is due on Sunday, April 21st at 11 p.m. Okay, so at this point, let us take a look at what we are going to discuss in today's session. Abraham, can you let us know what are we doing today?
Today's topic concept, amines, nomenclature, synthesis of amines, Boltzmann rearrangement, reaction of amines, Boltzmann elimination, diammonium reactions, and equivalence.
Thank you. Okay, just as Abraham has informed us, we are going to start our discussion of the chemistry of amines today. As you can see here, we do have a lot of topics and concepts to cover in this chapter. Okay, as usual, on the next slide, we have a list of learning outcome objectives. These are the concepts and or topics that you should master upon completion of the content of this chapter. So I will urge you to come back to this slide and use this as a study guide for studying for your quizzes and your exams. At this point, we want to ask, what are amines? Amines are organic molecules that contain nitrogen atoms. Organic molecules that contain nitrogen atoms, or atoms As you can see in the example on this slide, we have this molecule here. Containing the nitrogen atom. We also have this molecule, each one of these molecules contains nitrogen atoms. As you can also see, we have 4 different types of amines. We have 4 different types of amines. If you take a further look at this molecule, you will find out they are essentially derivatives of ammonia. This is an ammonia molecule right here. You could consider amines as derivatives of ammonia, and as we all know, ammonia is a very basic molecule because of the lone pair of electrons on the nitrogen atom. Ammonia could act as a base, it could also act as a nucleophile. So all of those features we are going to also see in all of the amines. As you can see here, we have 4 different types of amines. We have what we call the primary amine. In the primary amine, what have we done? We replace one of the hydrogen atoms with a carbon atom, right here. And then we have secondary amine. In the secondary amine, we replace 2 of the hydrogen atoms with 2 carbon atoms. So that is a secondary amine. Then in the tertiary amine, right here, what we have replaced all of the hydrogen atoms in ammonia with carbon atoms. So that is a tertiary amine. Okay, then finally we have what we call the quaternary amine. Here, not only have we replaced all of the hydrogen atoms with carbon atoms, we have also replaced the non-bonding pair of electrons with a carbon atom. So this is now the nitrogen atom in the quaternary amine is positively charged. It has a formal charge of +1. So these are all of the 4 different types of amine that we are going to encounter during the course of our discussion. Okay, on this slide, I want to show you a few more examples of amines and also begin to show you the nomenclature of amines. You can see here, this molecule here, called trimethylamine. This is the molecule that is responsible for the fish odor. When you go to the fish market and the market is smelling, this is what is smelling right here, this molecule right here, trimethylamine. Of course, this is the active ingredient of tobacco, this molecule right here. I'm hoping none of you smoke cigarettes, because this is a molecule has been implicated in all kinds of health matters. Also here, another molecule containing nitrogen atom. This molecule here we call cocaine. Once again, I do hope that none of you, you all know what I was going to say, right? I do hope that none of you have any experience with this molecule. Yeah, this is a very dangerous molecule, of course. So anyway, now let us get to the nomenclature of amines. Okay, for the nomenclature of amines, there are 3 different types of IUPAC nomenclature that we use for amines. So let us use this molecule here to demonstrate those 3 different types of IUPAC nomenclature for amines. Say, for example, we have this molecule here. This is a simple amine. Now, what type of amine will this be? What class of amine is this? This is a primary amine. Very good. Now, if we want to name this molecule in one format, let us say, okay, I told you we have 3 ways of naming amines. Okay, the first one, you take a look at in the case of this simple amine here, you take a look at the carbon chain that is attached to the nitrogen. and then you give the name of that alkyl chain. In this particular instance, what would be the name of the alkyl group here? Okay, so you then say butyl. You give the name of the alkyl group, butyl, and then you add the word amine to the name, to the alkyl name, and this will be one word. So this becomes butyl amine. In the second type of nomenclature, we have, okay, that is the first type. I told you 3 types, right? Okay. In the second type, we could name this amine here as a derivative of the corresponding alkane. In this case, the corresponding alkane would be what? Butane. Very good. The corresponding alkane would be butane. So what do? We remove the E ending of the corresponding alkane and we replace with amine. So this time becomes butane amine. Now both of these are, I'm sorry. Butane amine. Now both of these are accepted aliphatic nomenclature. Now in the third type of nomenclature, we could also name this as a derivative of the corresponding class of compound that you find in this molecule. In this particular instance, the corresponding class of compound will be a butane, will be a hydrocarbon chain, which is the alkane. So therefore, we are going to name this as a butane. So when you do that, then this group here becomes an amino group. That becomes an amino group. So if you want to name this as a derivative of butane, what would be the name? This would be scenario number 3. What would be the name? Okay, the amino group would be the substituent, just like your methyl group or ethyl group. So what would be this name? One amino butane, exactly. So it would be 1 amino butane. So those are all of the 3 different ways of naming amines. Now, of course, if you have this, there are certain names that are accepted. There are certain common names that are accepted as aliphatic names. If you have this molecule here, okay, the tendency for us is to name this as phenylamine using this scenario right here. But instead of calling this phenylamine, we use the common name. And what would be the common name for this? You've seen this before. Aniline, exactly. So the aniline. So for this class, you use this name aniline to describe this molecule here. Okay. Okay, let us give you a couple more examples of nomenclature. So therefore, supposing I give you this molecule, giving you those 3 formats for naming amines, what would you call this? What would you call that? Use any one of them. What would you call that? Use the first one. Cyclohexylamine, very good. So this could be cyclohexylamine. Now supposing I have this. Supposing I have this secondary amine right here, okay? In this case, what do? Of course, you look for the longest carbon chain that is attached to the nitrogen atom. You use that for the base name, or you use the more complex fragment as the base name. In this case, we want to call this cyclohexylamine as the base name. Okay? So therefore, if we are going to call this, the base name will be cyclohexylamine. And then to indicate that we have a methyl group attached to nitrogen, we simply do this. Say N, so this becomes N-methyl cyclohexylamine. You notice here, this is your base name. And this here simply tells us that the methyl group is attached to the nitrogen atom. Now, supposing we have this. Supposing we have this. Now, what class of amine is this? A tertiary amine. Okay. Now, what will be the accepted hydrofrac for this? N. Okay. So the base name will be. You want to use this for the base name, right? This part of the molecule here, right? So that would be, how many carbon is that? 5. Okay, so that would be pentylamine, right? And so therefore this name becomes what? N. You have to follow alphabet attached in order. N ethyl, N methyl, pentyl. Very good. Or you could say pentamine if you if you want to use the second scenario. Okay, so in this case we say pentylamine. Okay? So the nomenclature for amine, any one of those methods for naming amine will be acceptable. So at this point, let us begin to look at the synthesis of amines. Okay, I'm going to tell you most of the synthetic methods we have done before. So many of them will be a review to all of you here. Okay? So to make it easy for you, I'm going to number them. Okay, synthesis of amines. Let us use for the first one. Okay, I will say reduction of nitrite. Reduction of nitrite. We've done that before. If, for example, you take this molecule here, which will be a nitrite, and you take lithium aluminum hydride, step 1, LAH, lithium aluminum hydride, and step 2, dilute acid. Okay, what you have here, you are going to get a reduction, addition of hydrogen across the carbon-nitrogen triple bond. So you end up with this here. In this case, you get a primary amine. Okay, let us give you one specific example. We take this here, lithium aluminum hydride, followed by hydronium ion, and we get this primary amine. I should also let you know that this reduction, you could also carry out this reduction using hydrogen and a catalyst, like hydrogen and platinum. Okay? Or, I would say, or, you could also, or hydrogen with platinum. Okay? So the hydrogen with platinum could also reduce a nitride to give you a primary amine. Now, of course, we know how to make a nitride. You could get, you could obtain this nitride, for example, by an SN2 reaction, right? We all know that. SN2 reaction between a primary substrate and a cyanide, potassium cyanide or sodium cyanide. Okay. In this case, the cyanide will act as a nucleophile, displacing the bromine in an SN2 reaction. So that is one method for making amines. Another method for making amine will be the reduction of primary amides. Reduction of primary amides. Here, take a primary amide, react once again with LAH. We've done this before also, followed by hydrogen ion. This point you reduce the carbon oxygen double bond to a methylene group or a CH2 group. So it becomes another method for making primary amide. Of course, we know that we could make the amide from here, from an acid chloride. Okay. With ammonia. So this would be an acyl nucleophilic acyl substitution reaction, going from the acid chloride to the primary amide. Nucleophilic acyl substitution reaction. Of course, we also know that we could make the acid chloride from what? How do you make the acid chloride? How do you make the acid chloride? Carboxylic acid, very good. So we could make the acid chloride from the carboxylic acid using thionyl chloride. Okay? Just to give you one specific example, we take this here. Take this primary amide, react with LAH, and follow with hydronium ion. You get your primary amine. Okay, so far we have given you two methods for making for making amines. Now, a third method. Yes. I'll go back, okay. Okay, let us take a look at the third method for making amines. Okay, I will call this reduction. Once again, reduction of azides. This is new to all of you. Reduction of azides. Now, this here, this molecule here, or this species here, okay, this molecule, think of it as N3, which is negatively charged, because if you look at this, it has a net charge of it has a negative charge, because you see here you have a negative charge on this nitrogen and a negative charge on this nitrogen. However, you do have this nitrogen is positively charged, so there is a net charge of -1. Now this molecule here could act as a nucleophile. Indeed, it is a very powerful nucleophile. So the way I want you to look at this molecule the same way you look at a chloride or a bromide. Okay, it's no different from that. Okay. Now, so therefore, if I have this, how do I make an azide? I just told you, think of it as a chloride or bromide, right? It is such a powerful nucleophile that you could use the azide. Generally comes in form of sodium azide, just as you have sodium chloride or sodium hydroxide. You could use the azide in an SN2 reaction to displace a leaving group that is attached to a primary carbon. Okay? So here, what do we have? So you could make an azide that way. You could simply do that. Okay? Or if you want, you could simply write it this way. Okay? You could do that also. Now, if you have an azide, let us use the generic azide here. If you reduce an azide with lithium aluminum hydride, LAH, followed by hydronium ion. Okay, what you do here, you get plus you release nitrogen. Okay. For now, you guys, anybody who wants to know the mechanism of this reaction should see me after the class. But the net process here, the net process here is that if you take a primary an azide, you reduce with lithium aluminum hydride, you get a primary amine, and of course you release nitrogen molecule. Okay, an example would be a propoazide reacts with lithium aluminum hydride followed by hydronium ion. you get propylamine. Also, this is a method for making primary amine plus nitrogen. Okay, so far we have given you 3 methods. Now let us take a look at method number 4. Okay, method number 4 will be Gabriel synthesis. Gabriel synthesis is essentially using what we call phthalimide in an SN2 reaction phthalimide in an SN2 reaction. Now, what do we mean by phthalimide? If I have this molecule here, okay, if I have this here, okay, so we have this phthalimide here. Now, because this nitrogen here is attached to 2 carbonyls, therefore this hydrogen is going to be very, very acidic. So we could use an hydroxide, potassium hydroxide, for example, to deprotonate this hydrogen here. And when we do that, what do we have? We have you have this here. So this is negatively charged. So this now, we call this potassium phthalimide. Now this potassium phthalimide will act as a base. In other words, it could abstract an hydrogen and go back to this molecule here, or it could act as a nucleophile. So here, supposing now at this point, we have this primary substrate, ethyl bromide. Okay? So at this point, we are going to get an SN2 reaction here, where this simply comes here, attacks this primary carbon, and in so doing, the bromide is going to leave as a leaving group. So what do we have? We have this here, N-ethyl phthalimide. And then once you take this N-ethyl phthalimide, because now we have alkylated this here, notice what we can do here. Your imagination is the limit here. You could use any variety of alkylating agent at this point. And then if we take the N-ethyl phthalimide that we have here, we simply hydrolyze this using potassium hydroxide or sodium hydroxide. What we are going to do, we will open up this here and we will end up forming this. So you form your primary amine, and in so doing, we release this what we call phthalate. Okay? Of course, our interest is this molecule here. So this is another method for making a primary amine. So you could use any alkylating agent as long as you are using your alkylating agent is a primary contains a leaving group attached to a primary carbon or a secondary carbon, because this is an SN2 reaction. Okay. Okay. So far we have 4 methods. Okay. Method number 5. Okay, method number 5. Okay, we have what we call the Hofmann rearrangement. Hofmann rearrangement of a primary amide. Of a primary amide. Okay, this is a very neat reaction indeed. If you have this, say we have this primary amide, and this is a general reaction, any primary amide, and you take bromine in the presence of hydroxide. The hydroxide could come in form of sodium hydroxide or potassium hydroxide. What you are going to get, you are going to get a rearrangement in which you will get this. And in the process, we are going to lose a carbon atom. This is very important. We're losing carbon dioxide. Once again, for those of you interested in the mechanism, you should come and see me at the end of today's class. But the point here, which is very important, is that in the Hofmann rearrangement, you end up losing a carbon atom in the original carbon chain in form of carbon dioxide. So therefore, if I have this, I have this primary amide, and I take bromine in the presence of hydroxide. Of course, water is there. What do we get? What will be the product? Cyclohexyl amine, exactly. You get cyclohexyl amine. Notice what we've done here. We've lost one carbon chain. We've lost one carbon chain. Now, supposing I ask you this question, just to see how we can stretch your imagination. Supposing I ask you this question. Supposing I say, how can you go from here, toluene, right, to aniline? Let's see, can we do that? How will you go from toluene, this here, toluene to aniline? Anybody wants to give me? Keeping in mind that we have to use the Hofmann rearrangement. What do you do? Ines? Okay, K-4. Okay, very good. So you want to start with KMnO4, potassium permanganate. to oxidize these two carboxylic acid. Okay, very good. So in a step we should do this. So you get this. Then what do you do with that? Huh? DCC and H. Okay, you want to do that. Okay, very good. Let's take this out of the way. So you want to form a primary amide, right? What makes you think that is the way to go? Because we are losing a carbon atom, right? Okay, very good. Okay, so you say DCC with ammonia, that is good. We've not used that in a while. Of course, you could also take these two acid chloride with cyanide chloride, form the acid chloride, then ammonia. You could do that also. Okay? So therefore, then you do this. Then, after that, you do what? You do your Hoffman, you see? So at this point, your imagination is the limit here, right? We do want you guys to think. Okay? Bromine and hydroxide, so therefore you get okay, very good. Okay, anyway. So that is method number 5, the Hoffman rearrangement. We could also use a related method called, this would be 6, Courteous rearrangement. Using acyl azide. Now, what will acyl azide look like? Acyl. We have an acyl group attached to azide. What will it look like? Acyl attached to azide, right? Okay. Okay, so you have this. This is your acyl group, right? And then you have your azide. You have your azide. Like I say, you don't have to write the azide in this form. You could simply just write N3. That is fine. Okay. So you have your acyl azide. Now, if you take the acyl azide, you apply heat. What it does, the acyl azide will rearrange to give you this molecule here. We call isocyanate. We rearrange to give you an isocyanate. Similar to plus, in this case, we also now lose nitrogen molecule. Okay. See what is happening here? This alkyl group rearranges to this nitrogen, okay, to form the isocyanate. And then, after that, you add water to this. You add water to that, you now are going to get your primary amine plus carbon dioxide. Okay, so this method is similar to the Hoffman rearrangement. Now, what is the similarity here? What would be the similarity? We're losing a carbon atom. Okay, so this method is also losing a carbon atom. Okay, so therefore, if I add this, I have this acyl azide. I apply heat. I get the isocyanate. And then from the isocyanate, I add water. Then I get the cyclohexylamine. Plus carbon dioxide. Notice that we are also losing carbon dioxide here. So that is method number 7. I'm sorry, method number 6. Okay. Okay, now number 7. Number 7, we say reduction of amines and in amines okay, we have encountered amines and amines previously, but just to recap, if you recall, if for example you have this, a ketone or an aldehyde, and in this case, say we have nitrogen, ammonia to this. This will give you an amine, which is a carbon-nitrogen double bond. This is an amine. Now, if you take this amine, we could now reduce this with sodium borohydride followed by water, and here we are going to get a primary amine. If you start with ammonia. Now, instead of using sodium borohydride, we could also use sodium cyanoborohydride. Okay, that happens to be a very mild reducing agent that we could also use, followed by water. So you could use any one of these to get the same. Now, supposing you want a secondary amine. Supposing you want a secondary amine. Here, let us use the same cyclohexanone. Now, instead of using ammonia, you use a primary amine to react with the ketone or aldehyde. Keep in mind this reaction, you could perform this reaction with the carbonyl of a ketone or the carbonyl of an aldehyde. So it is a generic type reaction. So here again, you will form an amine. Still an amine. And then you reduce the amine with the appropriate reducing agent, sodium borohydride, followed by water. Okay, Okay, this time you get a secondary amine. So this is the first method we have given you for making a secondary amine. Okay. Now supposing we want to make a tertiary amine. By the way, all of these methods here we call reductive amination. We refer to this as reductive amination. So amination simply means you are forming carbon-nitrogen bond. Okay, and then subsequently you do you perform a reduction reaction. In this case, adding hydrogen across the carbon-nitrogen bond for the most part. Now, supposing you want to form a tertiary amine, what do we do? Okay, supposing you want to form a tertiary amine, what do you do? Anybody? Exactly. You start with a secondary amine using the same reductive amination. So very good. Okay, so here, let us go back using as example again the cyclohexanone. Here you use a secondary amine. Now with secondary amines, what do we form? We actually form the enamine. We form an enamine this time. If you recall when we did this earlier, let me make this here. Let us make this ethyl. Okay, so we form an enamine. So reaction of a secondary amine with a carbonyl of a ketone or carbonyl of an aldehyde, you obtain an enamine. An enamine is almost like a vinyl amine because you have the nitrogen is attached to a carbon-carbon double bond. So now at this point, we could take, by the way, all of the reduction could also be performed by hydrogen and a catalyst is a platinum or palladium, or you could use sodium borohydride followed by water. In this case, you form a tertiary amine. Okay, so now that we are actually talking about enamine, I do want to also show you another aspect of the enamine. Yes. You have a question? Oh, now the enamine that you formed here actually could be used as a source of enolate anion. Okay, let me write this. Enamine can be used as sources of enolate anion. And you know what that means. If you can use it as sources of enolate anion, what does that tell us? We could therefore use enamine for alkylation, right? Now, because what happens here, if you take, for example, let us say we take this here, which is commonly used. Say we have this ketone here, and we take this molecule here called pyrrolidine. Okay, we will form this in amine because that is a secondary amine. Okay, from that pyrrolidine. Now, because of resonance, imagine that this non-bonding pair of electron on nitrogen, we could move that to here, and thereby moving this pi electron to this carbon here, and that is how you generate your enolate anion. That is something that is similar to enolate anion. The nitrogen becomes positively charged, and you now have this. Almost think of this iminium anion here. We call this iminium. It is analogous to the enolate anion. Now, you can now use this as an alkylating agent. Say we add in an SN2 type reaction, because this carbon now becomes nucleophilic, so you could get this. So now you alkylate this carbon here. Now to go back to your ketone, what you then do, the iminium anion that you have here, the alkylated iminium anion, this here that you have here, this now becomes iminium ion rather, that we form here, because this is positively charged. You can very easily hydrolyze this. Using dilute acid to go to here. So it is a very neat way of actually alkylating an alpha carbon. Okay? Notice what we've done here. We start with the ketone. We add this pyrrolidine. This pyrrolidine is generally used for this type of reaction. You form the enamine, and as a result of this resonance here, this carbon becomes nucleophilic, and you could then alkylate that carbon, and then finally you hydrolyze to remove the iminium ion, and you end up with your carbonyl, with your ketone. Now, this reaction I've just given you here is what you call a stock enamine reaction. In other words, anytime you take secondary amine, react with ketone or aldehyde, form an enamine, and then you use that enamine for alkylation, and then finally open up the iminium ion to get the ketone or aldehyde. That is called the stock enamine reaction. Okay. Okay. So far, I have given you 7 methods, right? Okay, I've got one more method to give you for the synthesis of amines. Okay, method number 8. Method number 8 is not really a practical method to use, but we do want to let you know it anyway. This will be SN2 reactions of ammonia primary amine or secondary amine okay, SN2 reactions of ammonia primary amine or secondary amine. Of course, for you to have an SN2 reaction, there must be what? What do you need for the SN2 reaction? So some alkylating agent, right? In which the leaving group is attached to a primary carbon or secondary carbon. Okay. Say for example, you could take this. You take bromoethane or ethyl bromide, and you take ammonia. So the ammonia could act as a nucleophile. So you get an SN2 reaction. So you obtain this molecule here. The primary amine. Now the problem with this reaction is the primary amine that you form can now come back and also react with this bromide. So you get this whole series of reactions. So that primary amine can come back and react with another molecule of the bromide. So the point here is, in this type of reaction, you get a mixture, and that is why very often this is not a very useful reaction. So you could end up getting this. Okay, and of course the secondary amine that you obtain here could further react with the alkylating agent to give you a tertiary amine. Okay, so therefore this reaction, it is useful to know, but this is not a good reaction synthetically. Okay, so far we have given you 8 different methods for making amines. So at this point, what is the next topic that we need to discuss? Reactions, okay. How much time do we have? Okay, you have plenty of time. Okay, so at this point, let us go to the reactions of amines. Reactions of amines. Now, most of the reactions of amine that we are going to deal with will be concerned with the reactions of aromatic amines. Okay? So let us start with the reactions of aromatic amines. Of course, the most common aromatic amine is aniline. If you recall, when we did the aromatic compound chemistry, we gave you different substituents that would direct an incoming group to either the para position, auto position, or the meta position. Okay, if you still recall that, what kind of director is the amino group? It is an auto-para director. Very good. The amino group is an auto-para director. We also know that because this amino group contains this non-bonding pair of electrons, it is able to pump electron into the ring system. So it is an activating group, right? It is so activating that if you take bromine, you don't need a catalyst. Ordinarily, whenever we want to do electrophilic aromatic substitution in with aromatic compounds, what do? We need a catalyst, bromine in presence of iron 3 bromide. But in this case, with aniline, you don't need a catalyst. So if you have bromine dissolved in water, right away you see a precipitate form, right, just instantly, if you do this in the lab. And not only do you get the reaction, a bromination of the ring system, this is what you get. You get bromine here, you get bromine here. The amino group attached to benzene is so reactive that you cannot stop this reaction with monobromination or dibromination. You get tribromination. That is how active the amino group is. Okay. Now, supposing you want to stop this, supposing this is what you want to make. Supposing you only want to do a monobromination. Supposing this is what you want to make. It doesn't say you want to make p-bromoaniline. Okay? Now, what do? What you want to do, you want to deactivate the nitrogen, the amino group. Okay? You want to deactivate the amino group. To deactivate the amino group, what to do, you will do what we call acylation of the amino group. You acylate the amino group in order to deactivate. So, deactivate. In order to deactivate the amino group. Okay? Okay, and how do you do that? You take this here, take aniline. You guys have seen this reaction before. Now we are going to perform a nucleophilic acid substitution reaction. Using this time, we could use acetyl chloride or acetic anhydride. If you recall, when we did the reactions of carboxylic acid derivative and reaction of acetic chloride with aniline, what do you expect to get? What class of compound? Okay, you're going to get the amide because you are going to replace the chlorine, right? So you will get the amide. You get, in this case, a secondary amide. Now, the point to be made of this, once you obtain this secondary amide, right here, because of the resonance contribution from this carbonyl, drawing electron away from this nitrogen, this group here is no longer as activating as if it was just the amino group. So therefore, this group here, let me do this here, this particular group, we call this, we use it for deactivating the amino group. We call it the amino group. Okay, we use that group. We call it acet amino group. Now, we could now take this here the acylated aniline molecule, this here, sorry about that, the acylated aniline molecule, you can now take this, and now we perform our reaction, bromination. Okay? This group is still very active. It's still very active. You now perform your bromination. Now, because of the bulkiness of this group, this acetamide group, it directs an incoming group preferentially to the para position, unless the para position is not available. You might get some auto product, but that will be very small. So what do you get? You get this. So you get this. Now, to now show you what we can now do, now once we get this product here, keep in mind this is what we want to make. Okay, now we'll now take this, just hydrolyze this, potassium hydroxide or sodium hydroxide in water. That will open up the, you are now going to do what we call, once again, a nucleophilic acyl substitution reaction. The hydroxide comes here, attack this carbonyl. When you reform the carbonyl, this opens up, and then you are going to regenerate the amino group. You see how clever the organic chemist is. You all don't believe that, right? Okay, so now that molecule that we were not able to make because of the reactivity of the amino group, now we could make it by deactivating the amino group by acylation, and then we perform the bromination, and then we hydrolyze to remove the AC group. It's almost as though we are using the AC group as a protecting group, in a way. And then we could then use it to direct an incoming group to the para position. Okay? So anyway, this reaction we've given you here also is a general reaction. Acylation reaction is a general reaction of all amines. Okay? You take all amines will undergo acylation reaction with the acid chloride. For example, if you take this benzoic chloride here and this amine, of course you will get this. So this is a general reaction of amine. Okay? So this is acylation. Okay, now before we leave, I want to give you a very, very important reaction. This you definitely will be using this reaction. Okay? Definitely, you will be using this reaction. Okay, I say diazotization of of the aromatic amino group. Okay? Let us go back to aniline again. I take this aniline. If I take aniline, and I take this here, I take nitrous. Keep in mind, this is nitrous acid, not nitric acid. This is different from nitric acid. Nitric acid is HNO3. Nitrous is HNO2. In the presence of sulfuric acid, or sometimes you may use hydrochloric acid, you get this here. This very useful intermediate molecule. Okay, get this molecule here. Okay, okay, so you get this diazonium, what we call the diazonium ion. The diazonium ion, of course, it is also you have the counter ion here. If you use sulfuric acid, you may have sulfuric acid in solution, or chloride ion as a counter ion. So you get this diazonium ion. Now this diazonium ion is very, very important. You could very simply just write it, diazonium ion as this here. Sorry. Okay, just do that. That's diazonium ion. Okay. Now let us now take a look at the reactions of the diazonium ion. Reactions of diazonium ion. Now this series of reactions, we call them the Sandmeyer reactions. If you take a diazonium ion, now we know how to form the diazonium ion, right? We form the diazonium ion by reaction of the amino group with nitrous acid in the presence of sulfuric acid or hydrochloric acid. So you have the diazonium ion. Diazonium ion could react with sodium iodide in the presence of a copper 1 salt to form this. What have we done? We have replaced the amino group with iodine. Diazonium ion, you could react with HBr in the presence of copper 1 bromide. What do we get? So the next process here, we have now replaced the amino group with a bromine atom. We could take the diazonium ion, add sodium cyanide or potassium cyanide in the presence of copper cyanide. What do we have? Now you begin to see the versatility of this reaction. Now what have we done? We have now replaced the amino group with a cyano group. Now what can we now do? Supposing we now hydrolyze the cyano group, so now we've gone from the amino group to a carboxylic acid. Now what have we done here? We have now introduced a new carbon bond into the carbon chain. So this now gives us an opportunity to form a new carbon-carbon bond. Okay? On all of this we call Sandmeyer reaction. Okay, give you more examples of. We take the diazonium. Now you begin to see where we're taking you now. We take the diazonium ion. Diazonium ion, right? Equal complex with let me see here. Equal chloride here. No, just okay. Diazonium ion with copper oxide in the presence of copper nitrate. Yes. Oh, I thought somebody was calling me. Okay. Now, at this point, what are we going to do? What have we done? We have now replaced the amino group with hydroxide. You see the utility of this reaction. Now we could do this. We will use hypophosphorus acid. Hypophosphorus acid, this here, hypophosphorus acid. Now, if you do that with diazonium ion or salt, sometimes we refer to it as diazonium salt, what do? We replace the amino with hydrogen. You will ask me, why would you want to do that? Why would you want to do that? How crazy can you get? Okay, now this is why. So, okay. So these are all the various reactions of the diazonium ion, right? Now, okay, you got this? One more reaction, there will go. This is very important. One more reaction. Okay. Supposing you have to make this. Supposing I tell you to make this molecule here. We do this here and then we go. Supposing I tell you to make this molecule here. From benzene. Okay, there is no way you can make this molecule here from benzene without the diazonium ion. Because all of these bromine here, they are all auto-para directors. And all of these bromine here, their relationship are what? They are metal to each other. So therefore, for you to make this, what do? If I say make this from benzene, for you to do that, of course you want to make the amino group, right? How do you make the amino group? You do the nitration first, right? Remember nitration? And that gives you this. That gives you nitrobenzene. And then you take nitrobenzene. How do you go from nitrobenzene to amino group? What reagent do you need? You could use LAH. You could use hydrogen. Okay, very good. You say hydrogen, platinum, right? Or you could use iron in HCl. So that will give you the amino group. Now, you now take this aniline, right? React with bromine in water. What do you get? React with bromine in water. Exactly. Remember we told you that the amino group is so reactive. So you are going to get this. Right? because the amino group now is a directing group, direct to all those positions, also para positions. Now, what do you now do to get your product? Hypophosphorus acid, right? No, I'm sorry. From the diazonium ion. Step 1. And then step 2. Hypophosphorus acid, right? And that gives you what you want. Because at that point, you are now replacing the amino group with hydrogen. That is why the whole idea wasn't that it's not that crazy after all. Okay? So the diazonium reaction is a very, very important reaction in organic chemistry. So at this point, we have come to the end of today's session. You guys enjoy the rest of your evening.
Thank you.